Good evening everyone and welcome to IFAS. Good evening everyone. Good evening Nisha, Rohini, Hani, Rutuja, Leela, Pratyusha, Nisha. Good evening all of you, and I welcome you to this particular program that IFAS is running, wherein we are also going to conduct all the lectures in English. Alright, so a lot of students often request us to actually teach in English and not in Hindi or in English, which we normally do, because sometimes they are not confident in Hindi. They don't understand Hindi very well because it's not their mother tongue, but they are more comfortable in English because in colleges they have been learning in English. And for all such students, we are starting this new series wherein I'll teach quantum chemistry in complete English. I will not use a word out of the English language. I'll only use the English language. All right. Good evening, Pooja. Good evening, Kanchan, Pavan, Shubham, Vishnu. Good evening. Is this section under Jazba 1.0? Yes, but this is Jazba 1.0 English lectures. All right. These are Jazba 1.0 English lectures. Okay. All right. So welcome all of you. Welcome to these classes. And in these classes, I'm sure. So first of all, let me assure you that even if you don't know English, even if you think that you are not very good in English, even that is not going to be a problem, because I assure you that I'll make things so simple that the simplest of English will be sufficient for you to understand this entire course. All right. Because language should never be a barrier in understanding chemistry or physics or whatever your subject is. The language is just a medium, is just one technique in which we learn science. So which is why I'll ensure that the language is so simple that each and every one of you will understand this perfectly. Okay. All right. Yes. So good evening everyone. Good evening Shubham, and welcome everyone again. Now, the topic that we are going to study today is quantum chemistry. We are going to start quantum chemistry, and this is going to be a lecture series where we are going to look at not just the syllabus which is necessary for the various entrance exams, which is CSIR NET, GATE and SET exams, or BARC or TIFR exams, but typically you'll realize that when you look at the TIFR question paper, all right, especially the TIFR question paper, I won't talk about the NET and the GATE papers. In the TIFR question paper, the questions sometimes can be very long, and they are in English. They are long questions, and the only reason that we fail to solve them is because we don't understand the English part. We don't understand what's written there. So these lectures are also going to help those Hindi speaking students who will learn to understand these questions, these concepts in English as well, and that helps in a lot of these exams. Because what I've realized over the years is that students are unable to solve questions simply because they don't understand the language of the question. The moment someone explains them the question in their native tongue, they immediately solve it. And that's exactly what we are targeting here. We are targeting that you understand these concepts in English, you understand them so well that you never will start thinking that language is a barrier. Okay, and for that purpose, I am going to, I'll tell you right in the beginning, I'm going to use the reference book, which is Atkins. All right, so the one reference book that I always follow is Atkins Physical Chemistry. It's Atkins Physical Chemistry. Okay, it's Atkins Physical Chemistry. And this is the one book that I know that a lot of students have heard from me that this is the best book, but they have also heard from their seniors, they have also heard from their teachers that the language in this book is tough. All right, so maybe use some Indian author, but I assure you there is no better book than Atkins Physical Chemistry, and the language is also not tough. The language is not at all tough. The only thing is you should start. The moment you start, you will go ahead. All right. So remember that to climb an entire staircase, you have to start from the first step, and the first step is that you have to trust that once you climb the first step, you will be able to climb the second, you will be able to climb the third and the fourth and the fifth, and you will reach the top of the staircase. All right. So you just have to trust in yourself that you will be able to do it, and you just have to start doing it. It's okay if you fail once in a while. It's okay if you don't succeed, if you have challenges, but facing challenges is what makes you stronger. All right, remember that a smooth sea never makes a skilled sailor. So if you want to improve your skills, you have to stop trying to swim or trying to sail in smooth waters. You have to try and conquer the storm that is there in front of you. Okay, there's a storm inside you also, and that storm is what is going to lead you to success. All right, so let's start by facing our challenges. Let's start by facing our fears. Let's face our fears together, and I assure you that you will come out of the other end much better, much more skilled, much more confident. Okay, and that's the most important ingredient in conquering any competitive exams, and that ingredient is confidence. It has nothing to do with your knowledge of chemistry, because I'm sure that all of you have that knowledge of chemistry. The necessary knowledge, you already have that. You don't need anything more. All right, but what you need is confidence. And if you have confidence, even with less amount of knowledge, I assure you that all of these entrance exams are in your pocket. You don't need to worry about these entrance exams. All right, quantum is very basic level. Yes, quantum is the most fundamental subtopic in chemistry. All right, and if you understand quantum chemistry, you'll realize that it helps you in general organic chemistry as well. It helps you in understanding atomic structure and periodicity. It helps you in understanding chemical bonding also. All right, it helps you in understanding so many different processes, even in physical chemistry, that you will have many different concepts in chemical kinetics, in chemical thermodynamics, in statistical thermodynamics, which you will understand so much better if you understand quantum chemistry well. All right, so which is why this is a very important subject also, very important topic also, and that's the reason why I'm starting with this topic. All right. Yes, okay. Okay, good evening Meenal, good evening Achal, good evening Vishnu, Smita, Sangeeta, good evening all of you, good evening all of you. So what do you think quantum chemistry is all about? You have all heard of quantum chemistry. Confidence is missing while preparing, yes, but it's not missing, it's just hidden, and it's hidden inside of you. All right, you just have to bring it out, that's all. Confidence is not missing. I am sure that all of you have sufficient confidence, all of you understand all of this. The only thing that you have to realize is that you are capable, you will be able to do it. You have to keep telling yourself that you will be able to do it, and just work hard towards it. Okay, and yes, so much scoring quantum chemistry. Yes, quantum chemistry is extremely scoring. In fact, the weightage of quantum chemistry is sometimes 16 to 20 marks. Okay, up to 6 to 8 questions for quantum chemistry each year will be appearing in the CSIR NET. Okay, 6 to 8 questions worth 16 to 20 marks. And what I'm talking about is just the CSIR NET exam. If you look at the GATE exams, GATE exam also, there are 33 marks of chemistry, of physical chemistry is there. Of those 33 marks, approximately 10 to 12 marks is quantum chemistry, which means 25 to 30% syllabus or the weightage is quantum chemistry. So that's a huge amount of weightage for such a topic, and it's obvious because it's a very fundamental topic. And once you understand this, your understanding of chemistry is going to go from here right to there, and that's what you have to aim for. All right, start from basic, because BSc level I not study properly. Yes, I am going to start from very basics, and in fact I am not just going to start from last year or 2 years back when you were in BSc. I am going to start 400 years earlier. All right, so we are going to start our journey into quantum chemistry 400 years before. Okay, in fact, this is a journey which starts from the first scientist you remember, the first big scientist name that you remember. And what was his name? His name was Isaac Newton. Okay, his name was Isaac Newton, and we are going to start our journey from Isaac Newton. But before we start, I would just like to remind you that the CSIR NET exam might happen in December, might happen in January, and there's not much time left for that exam. And if you want to start preparing for that exam, we have an exclusive English version batch starting from 17th October, which is today. All right, and this batch has all lectures only in English. And I welcome you to enroll in this course because there's a flat 70% off. There's a flat 70% discount on this course. Okay, just use the promo code ITIHAS. Okay, let's create history together. ITIHAS in Hindi means history. Let's create history together and enroll in this course. Let's get 100% JRF qualifications. Okay, and in fact, there is one more thing that I would like to point out. If you look at this, all you have to do is qualify JRF and send us your scorecard. If you just send your scorecard, we are going to return 100% of your fees. So you will get your entire fee amount back the moment you send us your scorecard. All right, so that's a big incentive for all of you, that you get to qualify CSIR NET JRF for free. All right, so first of all, there is a flat 70% discount. On top of that, there's a 100% scholarship for those who qualify JRF. All right, so let's create history together. You have never seen such an offer in the history of IFAS, not just IFAS, but any other institute. No other institute is offering this. And the reason why I say this is, if you look at the actual 6-monthly fee, if you look at the fees for the next 6 months, the 6-month subscription used to cost 17,500. Now we have knocked off the one, and it now just costs 7,500 rupees. Okay, so you can get the entire live course for just 7,500, and I'm sure that you will agree that no one else is offering you a full 6-month subscription at this price point. Okay, and that too for a regular premier class, wherein the recordings of these classes are also available. The daily practice problems, you will get practice problems for each of the classes that happen every day. Along with that, you have previous year questions. Along with that, you have teacher handouts, meaning whatever notes that teachers have made while teaching, they will be made available in the app as PDFs. And finally, you have also a regular Sunday test series. You also have a regular Sunday test series. All right. Please explain about weekly test. Yesterday's test I'm unable to write. I'm not getting at where. Right, yesterday's test I'll have to check again. All right, Inzamamul Haq, you don't have to repeat the same comment 5 times. I can read it once. All right, so yes, we are going to complete quantum chemistry on YouTube. So this is a part of the Jazba 1.0 batch, wherein we are offering 100% discount to students who are not being able to enroll. All right, can I watch these lectures daily? Yes, absolutely, you can watch these lectures daily. All right, except tomorrow. Tomorrow this lecture won't happen, but day after tomorrow we are going to continue daily. All right, so you will see that these lectures have been scheduled. If you go to our channel IFAS Chemistry, you will find that lectures for the entire week have been scheduled, except tomorrow. Tomorrow I am not available, but these lectures will continue daily. All right, okay. All right, good evening, Rajkumar. Yes, thank you so much, and if you love us so much, please send us some hearts, some fire. All right, so learn quantum mechanics. Maths is a problem. I am weak in maths. Maths is not a problem. Maths is not necessary to understand quantum mechanics, because maths is necessary to derive results in quantum mechanics, but maths is absolutely not necessary to understand the principles behind quantum mechanics. All right. Hello, honey. Yes, welcome to Gujarat. Welcome to Gujarat. Okay, so who else is here? So Honey is from Gujarat. Who else is here? From where can I see students? Leela is, I think, from Odisha, right? Leela is, I think, from Odisha. Who else is here? So Ramakrishna, thank you so much. Rama, where are you from? Shubham, where are you from? Nisha, how about you? Inzamamul Haq, where are you from? Sangeeta, where are you from? Rinku, Rutuja, Pratyusha, Vishnu, Shubham, Yogi, Shabnam, where are you from? So can you please tell me in the comments where you are from? Okay, so Jaimini is from Gujarat. Welcome, Jaimini. Nisha is from Kerala. Welcome, Nisha. Shubham is from Dumka. Okay, where is Dumka? Simona is from Rajasthan. Hello, Simona. Leela is from Jharkhand. Oh, Leela is from Jharkhand. Okay, okay, okay. All right. Yes, I forgot. I think you had mentioned it earlier. I forgot. I'm sorry for that. Rama is from Telangana. Okay. Hello. Sangeeta is also from Telangana. Rinku is from Maharashtra. Okay. Okay. Inzamamul Haq is from Bihar. Nisha is from Kerala. Yes. Bharat is from Haryana. Bharat or Bharat, I think. Jazba class PDF and test series, they are being uploaded. So please have patience. I assure you that all of them will be available on the app. Just please have patience. We have already uploaded it on Saturday, but there is some technical difficulty because of which it's not visible. We'll get it done today itself. Okay. Shayoni is saying, sir, I'll give NET 2023 and GATE 2024. Am I eligible for the new batch in IFAS? Absolutely, Shayoni. We don't have just 6-month subscriptions. We also have 12-month and 24 months, which is a 1 year as well as a 2-year subscription. We are covering every type of student. We are also targeting BSc students who want to learn chemistry right from scratch from the best faculties in India. Okay, best educators in India are going to help you out, are going to teach you in these batches. All right. Hello, Shabnam. Okay, Shabnam is from Haryana. Hello, welcome, Shabnam. And Pratyusha is from Andhra Pradesh. Okay, hello, Pratyusha. Hello, Pratyusha. Hello, Meenal. Yes, Honey. Yes, okay, yes, Honey. I like everyone to follow Honey's example and motivate me by sending some love in the comments. Okay, now let's continue. Let's actually come back to our main point, which is quantum chemistry. Now, the title for this lecture, the title for this session was Classical versus Quantum. Okay, classical mechanics versus quantum mechanics. What's the difference between these two? Okay, there is something called as classical mechanics in physics. There is something called as quantum mechanics in physics or in chemistry also, in sciences in general. So what is classical mechanics? Classical mechanics sort of began with Newton's laws of motion. Of course, in our lives, it began from Newton's laws of motion. Classical mechanics is something that man has been observing in the day-to-day life for centuries now. All right. Now, what do Newton's laws of motion tell us? The first law tells us that a body in motion remains in motion, or a body at rest remains at rest unless acted upon by a force. All right. What does this mean? What this means is every object in the world is exactly like you and me. All right. So if you are watching TV and we are enjoying the program, we'll continue to watch TV. We'll continue to watch the program. We'll not even bother about eating. We'll not even bother about whether it's time to sleep or not. All right. We don't even care whether the exam is tomorrow. If we like the program, we'll continue to do that. If we are studying and the exam is tomorrow, we don't even stop to sleep. We don't even stop to eat because we are so afraid that we won't complete the syllabus that we continue to do it no matter what happens. Okay, so just like us, we continue to do the same thing over and over again for unless and until there is some disturbance. Someone, while you are studying, your friend comes and calls you to play or to go about town, to just go around roaming or to have cold coffee, and then you stop studying and then you go. But until your friend comes, until there is some disturbance, until there is something that shifts your focus, shifts your attention, you continue doing the same thing. And that's exactly what every body in motion does, or every body at rest does. A body in motion continues doing what it is doing. A body at rest keeps remaining at rest. Okay, if you are sleeping, we just want to sleep. We don't even want to get up. All objects in the world are exactly like this. Okay, all objects in the world are exactly like this. All right. Pratyusha, thank you so much. Thank you so much. Classic deals with larger bodies, not necessarily, Rajkumar. I'll come to that point also. So what you are saying is sort of correct, but not exactly. So Rajkumar is from Dhanbad. Okay, hello, welcome, Rajkumar. Shubham is also from Jharkhand, I think. Okay, because he is talking to Leela, just like so. Because we are trying to emulate a classroom experience here. Even all you students are also trying to behave as if you are in a classroom. When the teacher is explaining something, you are talking to someone else. All right. Shubham is talking to Leela because both of them are from Jharkhand. Meenal is from Rajasthan. Yes, Meenal I know very well. Meenal is a student from our batch, our online batch. Kanchan is from Uttar Pradesh. Welcome, Kanchan. Kanchan also regularly attends our lectures, but typically in Hindi. So this is the first time we are having a complete English lecture. All right, law of inertia. Yes, absolutely, Leela. Law of inertia. All right. Please provide information about updated MSET syllabus. Inspired by chemistry, the MSET syllabus hasn't changed a lot. The syllabus is quite similar. Only thing is they have just mentioned everything explicitly. That's the only thing. All right. So the syllabus is the same. Your MSc syllabus is your syllabus. Good evening, Yogita. Yogita, I just met today in the afternoon because Yogita is also our online batch student. So Yogita has been learning surface chemistry with us in our classes, and now she has come here to learn quantum chemistry as well. Okay, great. Yes, Pratyusha is also a student from the crash course. I remember you, Pratyusha. Not as if I have forgotten you. I just didn't remember which batch you were from. But yes, I know that you are a student of our online batches also. All right. Okay, so let's continue. Newton's first law of motion. This is the law of inertia. It tells us that the body continues to be at rest or in motion, whatever it is doing. It continues to do so unless acted upon by a force. Okay, your friend comes and calls you, distracts you, and then you go. All right, but till then you will keep studying. That's the point. The second law of motion, what does it tell us? Force equals mass times acceleration. Okay, all of us know F equal to ma. That's the second Newton's law. Third is, for every action there is an equal and opposite reaction. Obviously, we study hard, we'll top the exam. We don't study hard, we might not top the exam. All right. So every action has an equal and opposite reaction. All right. For example, all of you are liking this lecture. All of you love this lecture, and which is why you'll share this lecture. What you'll do is you'll just if you look at the button below here, there is a share button there. You'll just click on that share button, and you'll get a link, and you'll put it on your status, telling that Rajiv sir, for the first time IFAS is teaching completely in English. All right, and you'll put it on your WhatsApp status, or you'll send it to your friends. And as a result, what will happen? These friends will also join these lectures. They will come up with more points, and all of you know how group discussion, group study helps all of us. All right. So this is like group study. So when you share this lecture's link with all the students, they are going to come and help you learn quantum chemistry in a much better way. Okay, because if I explain something in a more complicated way, someone is going to ask me, sir, please simplify and explain, and that will also help you. All right. So every action has an equal and opposite reaction. Sharing is caring. So if you share, you will get back 10 times. All right. So if you like this lecture, if you like this particular session, it tells me that you are enjoying these sessions, you want more such sessions, and I'll keep bringing more such sessions for you. Okay, for every action there is an equal and opposite reaction. All right. So that's what Newton's law told us. But what it also told us was something called as trajectory. What it also told us was something about a trajectory. What do you mean by trajectory? Trajectory means that the path a particle follows. Okay, what the classical mechanics told us was that there is a trajectory, path followed by a particle. Path followed by a particle. Okay, and this word is also very important because Newton liked everything in the world being in this format. Newton liked everything in the world being in this format as particles. Okay, Newton liked if everything in the world was like a particle. Okay. All right, that's great, Mamata. Good evening, Mamata. That's great, Leela. Very good. Okay, like and share. Yes, absolutely. Okay, and what this tells us is, if we know where the particle is right now, we also, and if we know its velocity, we'll also be able to predict where the particle will be 10 seconds from now. Okay, so there are Newton's kinematic equations also, something that we have learned. And because Newton liked dealing in particles, what Newton thought was light is also a particle. What Newton thought was light is also a particle. What does this mean? That you see that this is the eye, there is a retina here. Okay, this is the retina. Retina means in our eye there is a sort of a screen there. On the screen the image is formed, and what Newton told us was, what Newton recommended was that light is consisting of particles. Light has a lot of particles, and these particles come in various sizes. Okay, these particles come in various sizes. All right, and you will see that if you look at these particles will be yellow in color. If you look at these sizes of particles, they will give you a green color. So an average size, light will have particles of all different sizes. But if you calculate the average size of all of these particles, you will start seeing different colors. Okay, there will be a yellow color, a green color, a red color, a blue color. Okay, so the moment you start thinking of light as particles, okay, and the moment you start imagining that different sized particles have different colors, or they represent different colors, what will happen? That's what Newton tried to explain with his next point, which is Newton tried to explain reflection of light using this. Okay, Newton tried to explain reflection of light using this. Okay, so how does light get reflected? Just like a ball bouncing off a wall. Okay, just like a ball bouncing off a wall. Now, how does a ball bounce off a wall? A ball falls, it retains that angle, and it bounces. So just like that, Newton's corpuscles, which are particles of light, Newton's corpuscles, which are particles of light, they fall on a reflecting surface and they are reflected, they bounce off the surface. And this is very easy to understand because we have seen balls bounce. So we know that just like balls bounce, light will also bounce. What's the problem there? There's no problem there. All right. And Newton didn't stop here. Newton thought that his theory was about corpuscular theory of light. It's called as the corpuscular theory of light because all these small particles that you see, these are actually corpuscles. These are what Newton called corpuscles, meaning particles. Okay, these are discrete entities. These are separate entities. They are separate objects. Okay, so light is composed of various particles of different sizes, each size particle representing a different color. That's what Newton suggested. And when this particle bounces from a reflecting surface and we observe it there, then we see that okay, light is coming from that direction. Okay, Newton could also explain refraction because we all know that inside water the world looks different. Okay, the world looks completely different when when we are underwater. Corpuscular means, so the word corpuscles, that stands for particles. Okay, the word corpuscles means particles. Okay, that's what it means, Leela. Okay, all right. Yes, thank you so much, Leela. You have already liked and shared, and I'd like everyone to follow Leela's example because all of you have seen, for every action there is an equal and opposite reaction. For every good deed that you do, you will get everything back. You will get someone else will perform a good deed for you. You share this video, you are sharing knowledge, someone else will share their knowledge with you, and what happens is when each and every one of us shares our knowledge grows, and which is why sharing is absolutely important. Okay, yes, so these are again, now what happens? Suppose you take a ball, okay, suppose you take a heavy ball and throw it inside water. Okay, you go to a pond, the favorite pastime that everyone has. If you go to a pond or a lake or a river, I am sure there are only two things that come into your mind. One is jump into the river, okay, play, swim there. Second is if you can't jump into the river, okay, there are some people who can't swim. So what do? The first thing that they do when they go to a river is they pick up a stone and they start throwing stones into the river. Of course, right? And all of you have, you must have observed that if you throw a stone into a river, it will not follow the same path. In fact, the stone goes like this, and inside water it changes direction because water is thicker, water is more viscous. Okay, so what it does is it does not allow the particle to retain the same kinetic energy that it had earlier. So what this particle will start doing is it will change its direction. Okay, because now a part of its kinetic energy has been taken up by water. All right, and hence water does not give it the same horizontal component of velocity, so it will slow down in the horizontal direction and it will change its direction. And that's exactly what particles of light do when they go from air to glass. If this is air and this is glass, light particles go and fall on glass. Glass is a thicker optical medium, okay, its optical density is higher than air, and which is why light will bend, light will change its path, and that is what is called as refraction. All of us have learnt this. That is exactly what is called as refraction. Good evening, Chief of the God. Pata nahi chala, sorry. Okay, Chief of the God is saying, I don't understand what he's saying. He hasn't understood something. That's what he's saying. That I understand, but I didn't understand what he didn't understand. Okay. All right. So this is about refraction of light. In fact, because light is of different particles, because light is made up of particles of different sizes, we can also talk about dispersion of light. We can also understand dispersion of light by this method. What is dispersion of light? You have a prism, and you have particles of light going in that direction. What will happen is, because the red particles, okay, because the red particles are smallest in size, they will not deviate a lot, they will deviate the least. But because the blue particles are heaviest, they will deviate the most. Because the blue particles are heaviest, they will deviate the most. And you will also get green particles, which are of an intermediate size, which will deviate somewhere in between. Okay, which will deviate somewhere in between. Okay, so this is essentially what is called as dispersion of light, or what we call as creation of a rainbow. Okay, this is how a rainbow gets created. This is how a rainbow gets created. Okay, this is how a rainbow gets created. All right, and Newton was also able to explain this. This is similar to physics. Yes, this is exactly physics. Okay, because we are trying to learn quantum chemistry or quantum mechanics. That is a part of physics. Okay, that is, all of that is a part of physics. So this is dispersion of light. And what happens is, because particles are of different sizes, the largest particles will change their direction most, and which is why the blue particles are changing the direction the most. The red particles are smallest in size, so they will change their direction to the smallest amount. All right, so this is what Newton was able to explain. But what happened later was, there was another phenomenon that scientists have observed, and which is called as diffraction. There's another phenomenon which is called as diffraction. So for example, you have light coming from this side. Okay, you have light coming from this side, and there is a small hole made in a cardboard. Okay, there is a cardboard or a paper, and we have made a small hole there, and from this hole, when light comes out, okay, you will actually see that light does not travel in a straight line. Light is also visible there, light is also visible here. Okay, for example, look at this. The central bright spot that you see, that's the size of the hole. Okay, the central bright spot that you see, that is the size of the hole. But you can see that there is light away from that bright spot also. So we expected that light will travel in a straight line and only be visible here. But the same light is also visible here, to a smaller and smaller extents. The intensity is lesser, but it is nevertheless always visible there. Okay, so light is always visible there. All right, is this clear? So this is what is called as diffraction. And somehow Newton's corpuscular theory, Newton saying that light is made up of particles, was never able to explain this. Okay, it was never able to explain what diffraction is. Okay, for obvious reasons, because why will particles on striking this start suddenly going in that direction? They will continue going straight. Either they will hit the wall and they will not be able to pass, or they will keep going straight. All right, so why will light be visible there? So Newton's theory was not able to explain this. And in fact, if we go further with diffraction, you also get something called as interference. Wherein, suppose you have these two slits. Okay, you have made two holes in paper. And from those two holes, light is going. And you can see that you will get a pattern here. In fact, if you see this is the actual photograph of an interference pattern. The central band which will be light going in the straight direction. Okay, what I would have normally expected was, if light goes from here, I will only be able to see light here. I will only be able to see light here. But what happens is, in fact, in both these places, you can see dark colors. In both these places, you can actually see dark colors. What that means is, light is not traveling in a straight line anymore. Light is actually bending, and what you can see here are interference patterns. In fact, you must remember seeing something like this if you are seeing on a seashore again, or a river bank, and if you just start doing this, okay, you start playing in water and you just start doing this, and you will see something like this emerge on the surface of water as well. Okay, and this is what is called as interference. Okay, this is what is called as interference. Okay. Tell about its principle. So the principle is the same, that from each of these slits there is diffraction of light happening, and when these waves interfere, you will get bright and dark spots. You will get bright and dark regions, and which is why you will see a pattern like this. You will not see light only in these two spots, but you will even see light somewhere here. You will even see light somewhere here. Okay, so that is what is an interference pattern. Okay, superposition of light. What is superimposition of light? Superimposition of light means two light waves on top of each other. So they add up, and when they add up, whatever new wave you get, that is the new light that you see. Okay, so that is what is called as superposition. For example, suppose we want to we are in a mood for a holiday, and we want to travel to the beach. Okay, we want to hire a car. Okay, but now what happens is, the car is expensive. The rentals are high. Okay, the rentals are high. So instead of just one person going there, what we'll do is, we'll ask 3 more friends. The more friends that we have, our cost also reduces, because the cab will cost lesser, the taxi will cost us lesser, and the more people are there, the more fun we'll have. Okay, if we start sharing our fun, sharing our trip, just like you have shared the link of this lecture, if we start sharing the fun doesn't become 4 times, the fun becomes power of 4. Okay, so it doesn't get multiplied by 4, it becomes the power of 4. Okay, just 2 people having fun and just 3 people having fun, 3 people have not 1.5 times the fun, but at least 3 times more fun. Okay, so that's exactly what is superposition. You have one wave of light, you have another wave of light, these combine. Okay, and when these combine, you get double the height. Okay, this wave was this height, this wave was that height, and now this wave will have a larger height. It will oscillate like this, and which is why we'll see a brighter intensity of light. Okay, we'll see a brighter spot here. Okay, all right, overlapping of 2 lights. You can say that it is an overlapping, but to be more precise, it is an addition of not intensities, but it is an addition of amplitudes. The intensity is proportional to the square of the amplitude. All right, so which is why it doesn't simply become double. The intensity doesn't double, the intensity becomes 4 times when 2 waves add up. Okay, and there are 2 types of superpositions also. There is constructive interference and destructive interference, but let's not go into that right now. Okay, all right, okay, let's continue then. So this is interference, and Newton's corpuscular theory is not able to explain. So what we needed was wave theory, and this explanation was given by a scientist called, or a physicist called, Young. Okay, Young's double slit experiment. Young's double slit experiment. Again, this is something that you have studied in your 11th class. In physics, you have studied this. Young's double slit experiment. Okay, and that is what explained interference. And there was someone called Huygens. Okay, there was someone called Huygens, and he was the one responsible for what we call now as the wave theory of light. Okay, Huygens tried to suggest that light must be made up of waves. That light must be made up of waves. Okay, Now we understand what happens with light. Now because light is waves, we have to also explain how light is formed. Okay, so there was a physicist again, his name was James Clerk Maxwell, and Maxwell gave 4 equations which changed physics completely. Okay, in fact when these equations started coming into picture, this was the time when physics and chemistry started to merge. Okay, earlier chemistry was you mix two substances, you get a third one, but you don't know why. All right, like for example, you take gold. Okay, you take gold or silver. Silver is much easier to observe. You take silver, okay, which is shiny, which is colorless. All right, or it is white in color. And then on the other hand, you take oxygen. Oxygen is colorless. It's in fact a gas. But when silver forms an oxide, it's neither colorless nor white in color, nor is it a gaseous in nature. In fact, silver oxide is a solid, and it's not even a crystalline solid or a metallic solid like silver itself. It is a solid, but a powdery solid, and it is black in color. Okay, so a combination of a colorless substance and a white substance gives black, and no one knows why. All right, this was the sort of situation till the mid 19th century. Up to 1850s, 1860s, no one really knew why we observe whatever we observe in chemistry. We just knew that there is something like this. All right, and in fact the periodic table started getting built much later, at the end of the 20th century or the end of the 19th century. The periodic table started coming into existence. Okay, Mendeleev refined the periodic table later on and made it into the periodic table that it is today. But at the end of the day, we needed something to merge physics and chemistry for us to understand that there are some things called as atoms or molecules, and the way to observe these atoms and molecules is electromagnetic radiations. Okay, electromagnetic waves are how we observe it. Light is an electromagnetic wave, and the basis of the entire branch of spectroscopy was given by James Clerk Maxwell's equations, and these equations suggested that light must be an electromagnetic wave. Okay, so now we have been bouncing. Earlier Newton called it particles. Light must be particles. Then someone came up and said interference and diffraction cannot be explained as particles, so they came up with a wave theory. And someone now refined the theory to say that okay, it's not just waves, it's electromagnetic waves, oscillating electric and magnetic fields. Okay, and this was actually proven by Hertz's experiment. Okay, so this is an experiment by a physicist called Hertz. This was an experiment by a physicist called Hertz. Okay, and what he did was he connected a metal rod. Sorry, he had 2 different electrodes, and in between these electrodes he created sparks. Okay, but he created sparks how? He applied an oscillating electric and magnetic field. Okay, meaning it's an alternating current. So what happens is some sparks jump there, some sparks jump back. Okay, and there is electrons go there, back, there, back, there, back. So the charge is also oscillating in nature. Okay, the charge is oscillating in nature, and if you have an oscillating charge, okay, if the charge goes up and down like this, all right, what you will see is that the electric field has started oscillating, and if this oscillating electric field starts traveling, then you can see that an electromagnetic wave is generated. So what Hertz was able to observe is that if you look at electric sparks, you can actually detect radio waves there. Okay, you can actually see radio waves coming out of electric sparks, and that is what told us that yes, light must be oscillating electric fields. Okay, light must be oscillating electric fields, and this entire electromagnetic spectrum is something that you have studied, starting from radio waves, which have the highest wavelength, then microwaves, infrared, visible, ultraviolet, X-rays, gamma rays, and then finally cosmic rays. Okay, so this entire electromagnetic spectrum was born with James Clerk Maxwell. Okay, and now there were other problems. So okay, fine, there are proofs that light must be a wave, electromagnetic waves. How to come radio waves? Because the oscillation frequency was close to the radio wave frequency. Okay, if the electric field oscillated at a much larger frequency, you would have gotten IR, you would have gotten UV, and so on and so forth. Okay, but because the current was oscillating at radio wave frequency, you got radio waves. That's what happened. Okay, high magnetic field in induction cell, sort of current perpendicular to magnetic field. Yes. Sound waves and light wave difference. Sound waves are not electromagnetic waves. Sound waves are matter, they are not even matter waves, they are actually waves which require a medium, but electromagnetic waves don't require a medium. Okay, Bindia is saying 70% of कब तक है, 70% of का office कब तक है, offer कब तक है. So what she's asking is where till when is this offer there? This offer will expire soon. Don't wait for the offer to expire, enroll immediately. Okay, so don't wait for the offer to expire. That's what I'll tell you. Okay, and now there are other problems that we ran into. The first problem was black body radiation. Okay, the first problem was black body radiation. And what does black body radiation mean? It doesn't mean radiation emitted by a black body. First of all, that's what you have to understand. It is not emission or light emitted by a black body. It simply is light emitted due to temperature of a particular object. Like for example, you can see that this is a container at temperature T. You can see it is silver in color. Inside there is darkness, but whatever light comes out of this is characteristic of whatever temperature that you have inside. And Rayleigh-Jean's law, okay, Rayleigh-Jean's law suggested that the intensity, Rayleigh-Jean's law suggested that the intensity of this light is inversely proportional to lambda raised to 4, meaning lower is the wavelength, higher will be the intensity, and which is why you can see that this graph actually keeps going up and up. If you look at the intensity, if you go to lower wavelengths, the intensity keeps going higher and higher. But what that means is, if you look at a person like me, my temperature is 37 degrees Celsius, 98.4 or 98.6 Fahrenheit, okay, and I should be emitting not just ultraviolet but X-rays also, because lower is the wavelength, higher is the intensity. So at the temperature that I am, I should be emitting X-rays, I should be emitting ultraviolet light. Alright, and which means if you are observing me, you should start getting cancer because I am emitting UV light. So that doesn't happen. What does that mean? What it means is this law is not completely correct, and which is where, so the experimental curve that we observe is something like this. It increases to a certain extent, and beyond that the intensity at lower wavelengths is smaller and smaller, which is why you will see me not emitting visible light but emitting IR light, infrared light. The temperature that I am at, 37 degrees Celsius, I emit IR, infrared radiations. Okay, sorry, ST rock boy, what is he saying? I don't know what he's saying. Okay, complete absorption of all lights. Okay, yeah, that's sort of a black body radiation. Correct, that's right. Okay, so now how did Rayleigh-Jeans derive this law? What Rayleigh-Jeans assumed was inside any object there are atoms or objects which have charges, and these charges oscillate at frequencies, but all possible frequencies. Okay, and when you start by assuming that when a charge oscillates, it creates electromagnetic waves. All right, and what it means is that these electromagnetic waves can have any frequency whatsoever. Okay, these electromagnetic waves can have whatever frequency that you want, and when that happens, you will end up with a curve like this. Okay, now what changed was when you start assuming quantization, of frequencies, you will end up with a graph like this. And as temperature increases, this graph moves to lower and lower frequencies, which is why lower wavelengths, which is why normally if you take a steel ball, it is emitting infrared radiation. But if you heat it, what happens is the emitted wavelength starts becoming smaller and smaller. The emitted wavelength starts becoming smaller and smaller, and which is why what you will start seeing is from infrared, its emission moves into the visible region. Okay, and in the visible region, you start seeing a red glow. Okay, you start seeing a red glow there. All right. So Rockbhai, he is asking me to speak some amount in Hindi, but remember, this particular class is for English only. Okay, this particular class is for English only. All right. Our Hindi lectures are at 5 p.m. and the English lectures are at 7 p.m. All right. The Hindi lectures are at 5 p.m. Nadeem sir is teaching chemical bonding there. Our English lectures are at 7 p.m. Okay, this is our English batch special. All right. So don't worry. We will teach this in English, in Hindi also, but at 5 p.m. All right. Okay, and this is called as Wien's law of displacement, and this is exactly what you see. And the main assumption that we have done here is that the energy of an oscillator, okay, the charge that is oscillating inside an object, that is quantized. E is equal to n into h nu, where now you know what h is. H is the Planck's constant, nu is the frequency, and when you assume this, you will get a curve like this, which means this is the first time quantization was predicted. This is the first time quantization was predicted. Okay, this is the first time quantization was predicted, meaning all possible frequencies are not allowed. And if this starts happening, there's another phenomenon that you will observe, is that in thermodynamics we have typically seen that for solids, the solids are always at constant volume. The molar heat capacity is 3 into R, okay, which is close to 25, per joules per Kelvin per mole. Okay, but what you will also observe is you start seeing that value only at high temperatures. You start seeing that value only at high temperatures. And in order to explain this, why this value will not be followed at low temperatures, in order to explain this, again what we need to assume is that the oscillators inside an object, they have to have only certain allowed frequencies. Okay, and this leads us to the photoelectric effect. Okay, this leads us to the photoelectric effect. All right, Hindi mein bhi boliye sir. Rutuja, again I'll repeat, this is an English version special class. So our Hindi classes happen at 5 p.m. This class is completely in English. This class is only in English. Right? Okay, and that leads us to the photoelectric effect. And this photoelectric effect now told us why light has particle nature. Okay, why light has particle nature. So we have been bouncing from particle nature, wave nature, and this will get back to particle nature. And this is what we will actually study or discuss in our next class. Okay, tomorrow there is going to be no class. Day after tomorrow there is going to be a class, and what we are going to study is how photoelectric effect explains particle nature of light. All right, so let me remind you once again before we stop this lecture. Our English special batch has already started 17th of October today. If you want to enroll, there is a great opportunity for all of you, and that opportunity is in the form of this flat 70% off. Use the promo code ITIHAS, ITIHAAS, and avail a flat 70% off in our exclusive English online batch. Okay, exclusive English online batch. All right, and don't miss this chance of studying from or learning from India's top educators, the best faculty for chemical sciences that you'll see in India. Don't miss the chance of studying with them, studying from them. All right, and ensure that your selection is guaranteed. Okay, ensure that your selection is guaranteed. Okay, so again, these are essentially the features of that batch and the fees for this batch for a 6-month subscription are 7,500 only. Okay, so thank you for joining me in this session. Let's take a break for tomorrow, and day after tomorrow we'll continue with our discussion about how light is a particle or a wave, or exactly what is it. Okay, all right. Rayleigh-Jean's law fails at short wavelengths. It's because oscillators can't have all frequencies, only certain frequencies are allowed. Okay, so let's stop today's lecture here and we'll continue on Wednesday. Until then, goodbye and happy learning. Keep watching our classes and keep learning from India's best faculties. Okay, goodbye everyone. Yeah.